Hi, I'm Jenna Larson, and this is my video for Lab 4, Physics 2212, where we'll be looking at magnetic braking with Faraday's law. Before we get into the nitty-gritty of it, just a little overview. The main purpose of this lab was to observe a bar magnet falling through a conductive tube of aluminum foil. And then after we did that, using GlowScript, we made a computational model of the same interaction, and then we compared those results. And the main results we got was an experimental fall time of 3.862 seconds and a computational fall time of 3.339 seconds. Now, just to start out, we'll look at a couple of the fundamental principles we'll be using. Firstly, we'll be looking at Faraday's law and Lenz's law. And then we'll also be looking at the magnetic flux and magnetic force, and we'll also be utilizing the Biot-Savart law and Newton's second and third laws. And just a little refresher on Newton's second and third laws. Those state that the net force acting on an object is equal to the rate of change of momentum, and that every action has an equal and opposite reaction. And then for the fundamental principles I mentioned previously, those equations can be seen on the screen. Nextly, we have the setup of our experiment. So basically, I got a tube of aluminum foil, and I held it upright and dropped a bar magnet through it. And I did this 5 times, and each time I recorded the amount of time it took for the magnet to reach the bottom of the tube. And then an observation that I did make is that the magnet did fall slower within the tube than it did within open space, so that definitely tells me there's some kind of magnetic forces going on in there. And then just some of the assumptions we made. We assumed that air resistance is negligible, the magnet remained upright while falling, aka it remained with north facing up. And then we're also assuming that the aluminum tube was completely non-ferrous. And these are the fall times that I got for the 5 times I repeated this, and then the average time I got was 3.862 seconds. Now to take a look at the GlowScript code we used to recreate this model computationally. Up here at the beginning of the code, you can see where I added in the physical values that I measured, the length, the width, the inner radius, and then the math to add those two. And then below that, you can see both the mass of the tube, the mass of the magnet, sorry, and then the magnetic moment of the magnet that I calculated in a previous lab. And then going down, we have the code that I wrote to create the dipole. And then we also have the flux calculation down here. And then on the right side of the screen is where we worked on creating the flux and the ring and just kind of the whole animation. And you can see the code that I wrote over there. And then we'll look at the results of this code on the next slide. All right, so the 2 images on the screen that we see now are the results that I got from the code I wrote previously. And we can see that we got a computational time of 3.339 seconds. And when we compare this to our experimental time, we can see that they're about 0.5 seconds apart. And some of the things that this could be due to is air resistance. We could have used more rings of current in the computational model, and then in real life could have done just a couple more runs to gather more data. And here, just a couple sources of error that I likely encountered during this experiment. As I've said repeatedly before, air resistance is in fact a real thing that should affect this experiment. I'm not a god when it comes to stopwatches, so I could have made some errors there. Also could have made someone measuring the properties of the magnet and/or tube. And who knows, maybe the tube wasn't completely non-ferrous. And lastly, just a couple questions to close us out. If holes or slots had been cut into the tube, how would this have affected things? Well, first of all, there would have been fewer rings of current in the tube, which would have reduced the force exerted on the magnet, and this then would have allowed the magnet to fall faster. Conversely, if the resistivity of the conductor were reduced as close as possible to 0, how would that change everything? Well, to first start, Ohm's law states that resistance and induced current are inversely proportional. And since we know that if the resistance were significantly decreased, then that means the induced current would be significantly increased. And then this increase in the current would create more opposing magnetic forces on the magnet, and this would cause it to fall slower. All right, that's all I've got for you guys today. Thank you for your time.